Hello and welcome to another video. In this video we're going to be working on a minimum falling path sum. And in the problem you're given an n by n array of integer matrix and you want to return the minimum sum of any falling path through the matrix. Falling path starts at any element in the first row and chooses the element in the next row that is either directly below or diagonally left right, specifically one of these three. So if we take a look at this first example, the best path is either 157 or 148, which gives you 13. So you basically can start at any one of these, at any single cell in the first row, and then every time you fall, you have to either go straight down or one to the left or one to the right. And you keep doing that and you want to find the best path. And so the second example is here, and this is the best one because it's negative, so you just want to pick the best negative numbers. And here the matrix length is n, so it's a pretty easy constraint, right? Like something like n cubed will pass. So essentially, this problem, you basically always have a choice, right? At every single cell you're at, you can fall straight down or left or right. And so when that's the case, you're pretty much always going to want to do DP. And it's a really straightforward DP problem, in my opinion. Basically, you have a choice between a couple things, and you're just trying to calculate the minimum. So that's like a standard DP problem, right? If you have choices and you're trying to get the count of all the paths, or calculate the minimum, or calculate all the maximum, and all your choices rely on previous choices, which they do here, right? Because every cell you're at relies on what decision you made before. So this is like a perfect example of DP. So for DP, you need three things. So let's fill those out. So 1, you need states. 2, you need a base case. And 3, recursive. So for the state, it should be pretty straightforward, right? We just need a row and a column, because we need to know like what cell we're at. And that's pretty much all we need, right? We just need to know what cell we're at, row and column. For the base case, it's also pretty straightforward. We basically are done when, like, let's say n is 3 here. We're done when we get to row n, right? So when we get to row 3, we're done. So here it's just going to be row equals n. And in which case, what should we return? Like, what's the path sum? Once we're done, well, we just want to return 0, right? So we can just return 0 because we're done. There's nothing else to calculate. And the recursive case is also very easy, right? So if we're at a row and a column, we can go to 3 locations. So we can go to 1 location is just the next row, so row plus 1, and the same column, or we can go left, so row plus 1, column minus 1, or we can go right. And you just basically have to check, can you actually go left or right? So let's say you're here, you can't actually go right because there's nothing here. A few ways to handle that. You can either have another base case where your row and column is invalid, and that's what I'm going to do. So I'll just say, like, if my column is invalid, let's return infinity, or you could check for that as you're recursing. Either one of those, pretty straightforward. So this is like a very, very, very straightforward DP problem. And yeah, that's basically all we need. And the other thing, when we recurse, we also need to add value of our current cell to one of these, right? So we're trying to minimize, we're trying to get the smallest value in these 3 things, and we always have to take the value of our current cell. So let's say, like, we start here, we have to take this one, yeah, we have to take this one. But then afterwards, we have a choice of these 3. So whenever you're at a cell, you have to take the current cell value, and then you just figure out, like, what's the cheapest left, down, or right. And yeah, that's pretty much it. So we can code it. So let's full screen. And so essentially, let's get n first. So we can say n equals length matrix. Then we just do a really straightforward DP, right? So you can have a cache, and then you just have a DP function that takes a row and a column. So like I said, in my case, I will just make sure that the column isn't out of bounds. So I'll say, like, if the column is out of bounds, then we'll return something that, like, we'll just return. If we're trying to minimize, the easiest way in dynamic programming to make sure that you don't use a value is just, if your state is invalid, just return infinity. If you're trying to minimize, and if you're trying to maximize, just return negative infinity. That way it'll never be used. So we can say if column is less than 0 or column equals n, it'll never be greater than n, so it'll just be these. We can just return infinity, which basically just means, like, invalid solution. Otherwise, if row equals n, then we're done and we just return 0. Finally, we have the cache case. So if row call in cache, we can just return cache row call. And then we have three choices, right? So we have the left, go down, and right. So let's take all those. So we can just say cache row column equals, remember we always have to take the cell that we're currently at, which is just going to be matrix row column. And then we take the minimum of the three paths. So we can say plus minimum of dp row plus 1, the same one, and then we just need 3 of these, so we can copy paste this. So now we can go left, which will be -1, and then we can go right, which will be +1. And yeah, so we do all this, then you just return it. So we can return this. And finally, we have to call our function. So the other thing is we have to call our function on every single starting column index, right? Because they said for the first row, you can start anywhere. So we basically have to loop through the first row and pass in every single column index in the row and get the minimum out of all of those. So we can easily do that. So we can just say result equals infinity. You could also just get these values. So you could do like something like this instead with the list comprehension. So you could say like result equals max of a list comprehension here. So you could say dp row, this is going to be 0 I, and then it's going to be 4i in range n. So what this will basically do is it will get every single value here for the column. So let's say you had like a 3x3 grid, it'll do dp of like 0 0, dp of 0 1, dp of 0 2, and you're just going to want to get the minimum. So actually instead of max we can get min, not mom. Okay. And I think if you don't make a list, it makes an iterator, I believe. Kind of like a for range loop is like an iterator, I believe. Not 100% sure. So you could do this, or you could make a list, but this is just like more memory efficient. It doesn't really matter for space complexity because the cache is going to be more than that. But yeah, so you could totally write it like this if you want to as well, if that makes more sense to you. Let's try this. Oh, we're not returning, so instead of result, we can just return here. Hopefully that's correct. Yep. Okay. So this does work. And yeah, and the efficiency, it's not too bad, but you can definitely optimize this. So I'll just do a quick overview of how we could optimize this. So notice we're always going down a row. And then for column, we're either going left, right, or down. So because we're always going down one row, our row only depends on the previous row. So I'll quickly draw what I mean by that, and then we'll do that. So let's say we have this problem. And our starting locations are 2, 1, and 3. Now when we go down to this next row, for every single location, we can just mark like what's the best one to go to, and that's what we'll save. Right? So that's basically how we're going to do it. So for every single one, we're just going to see like which one is the best. So what I mean by that is we're going to make a new row, and we can just make all these values infinity or something to start. It doesn't really matter. And so this is going to represent dp of this row here. Like what's the cheapest way to get through these things. Then for this, we just basically check. This is the row above. So for this, how could we have gotten here? We could have either gone straight down or we could have gone left, right? And what's cheaper out of those? So it's going to be going left. And then also you do need to include its actual value. So its actual value is 6. So this is going to be 7. Then let's fill out the rest of these. So like I said, you can initialize it to infinity. I'm not going to do that, but that's basically what it's going to go. So here, it's going to be the cheapest one out of these, which is 1, and its value. So 1 plus 5, which will be 6. Then here, it's going to be the cheapest one out of these two, because these two lead here. So that's going to be 1 plus its value, which is 4, so 5. So this is row 2. This is like the optimal row 2. Now we need one more row. And so for the last row, what's the cheapest way to get here using the 6, and what's its value? 7, so this is 13. cheapest way to get here is also, or cheapest way to get here is going to be 5, and its value is 8, so this is going to be 13. And here, cheapest way is 5, and its value is 9, so it's going to be 14. So these are basically the DP values of, like, if I wanted to get to each of these cells, this is what it would cost. And notice you only need to store one row at a time. So like to fill out this row, you only need this row. And then to fill out this row, you only need this row. So what we're going to do is we're just going to store 2 rows, and we're going to iteratively go down this. And then finally, our last row of numbers will be like our best result. And we just simply have to go through that and get the smallest one out of those. And that's going to be our answer. So a little confusing, but yeah, this is called bottom-up TP, and we're going to do a space optimized, so I'll link a video that's a little bit more descriptive. And if this is confusing, that's totally fine. If you can just make the memoization easy solution, that's like good enough. But if you do want to practice bottom-up, we can do that. So basically what I'm going to do is I'm going to make a DP array that's just going to be starting at row 1, right? So this first row, we already know the values. These are the costs of getting to all these things. So that's what I'll make my first row. So I'll just say DP equals matrix 0.copy. So we're basically just taking the first row of the matrix and copying it. This will be our initial DP, and then we're gonna loop however many rows we have left. So in this case, we have one more row here and one more row here. So we'll loop 2 more rows, get these 2 things, and then finally, and basically the whole point of this is, if this is 3 by 3, this isn't saving us much. But imagine this was 3 by, or instead of 3 by 3, imagine this was like 100 by 100. Then we're only keeping 2 rows, so then we are saving a lot, right? Because we basically eliminated the dimension from that. So what we are going to do is we're going to say, we're going to have a loop from 1 till the last row, pretty much, right? So this is row 0, so we just need to loop from 1 to the last row. So we'll say for, we can say row here if we wanted to, in range 1n, and every time we get to a new row, we're going to make a new array, and we're going to initialize it to something. We're not going to use the values. We're going to override the values, so that part doesn't really matter. I'm going to initialize it to 0, and then I'm just going to override all the values anyway. So we're going to say new DP equals this. Now we have an inner loop where we're basically, for every single value in this new DP that we make, we're going to figure out like what's the best way to get here, right? So we're going to figure out what values from the old DP can we use to get here, and then we'll just take the cheapest one and store it in there. So we can say for column in range n, we're essentially going to calculate the 3 values. So we're going to calculate, given a location, we're going to calculate the upper left, the upper, and the right. So we can call this maybe like left, up, right, or something like that. So left equals DP, and the location is going to be column -1, but we do have to make sure this is inbound. So if column has to be greater than 0, right? Because if we're here, there's no left. So if this doesn't exist, then we'll just make it infinity, and we're going to take the minimum of 3 numbers, so this is never going to be used. So we can do this. Then we're going to calculate the upper value, like up or something, whatever you want to call it, which is like the one straight above it. So up equals DP of the same exact column, and this is always going to be valid. And finally we have right, and right is going to be very similar to this. So DP of column +1 this time. If column, so column has to be less than n-1, right? Because if we are at this location, this is n equals 3. If column is 2, then you couldn't, there is nothing to the right. So you just have to make sure that your array is actually inbounds here. So if column's less than -1, else same thing. So now these are our 3 choices, and we just basically minimize those. So we can just say new DP column equals the minimum of these 3. And there we go. And so now that we get this, we are going to set our old array equal to our new one. So this is actually going to look like is kind of like this. So our old array will start here. Our new array will be over here. Then once we fill out our new array, we're going to say, let's make this DP now. And let's just delete this. And then we start over here again. This will be our new array that we're filling out. Once we fill it out, we'll get rid of this, and we'll make DP equal to this. So that's going to be the idea. So at the very end, we'll just say DP equals new DP. Now finally we have this array, and this array at the end is going to be the minimum cost of getting to all of these indices. Then we just return the smallest one. So we can just return minimum of this new DP thing. And so this is going to be a lot more efficient because we get rid of a dimension, plus it'll be tabulation, which will be faster. So this shouldn't be columns, this should be n. Oh, we did something wrong here. Oh, this should be DP. Hopefully that's correct now. Let's see. Nope. Okay, let's see what we did wrong. Oh, so we forgot one thing. So here, it's the minimum of the 3 values, right? So for here, it is the minimum of the 3 values, but we also have to include the actual value in the grid that we traverse. So that's what we forgot. So we just have to add that in the front. So we can say here, this is just going to be a matrix of this exact row and column. So row, column, plus the minimum of these 3 things. Okay, there we go. All right, and there we go. So this is a lot more efficient now, and it's a lot better in space as well. I will include both solutions, and I definitely think if you are starting with DP, I probably wouldn't even bother with this. But if you could do the memoization very easily, then if you want to learn something more difficult and more efficient, you can practice this. If you want to, you can actually make a whole matrix first instead of like doing these 2 rows. You can do that, and then from the matrix go to just the 2 rows. So I kind of skipped a step there, but it's going to be very, very similar. You're just filling out a matrix instead of this. So instead of these 2 things, you will just use a slightly different indexing, but the 2 loops will be the same, and all the logic will be exactly the same. So I just think it's kind of a good habit to be able to go from memoization to space optimized bottom up right away, instead of having to do like step by step by step, because it looks cool in the video, but you know, in an actual interview problem, or if you're actually doing this, you don't want to spend like 30-40 minutes on a reasonably easy DP problem. So I think being able to do it quicker is going to be better. Yeah, so let's go through the time. So the time here, basically we are looping, like this is row and column, right? So this is just n squared because it's a square. And the space, now we've reduced our space to ov n instead of ov n squared with our cache. And like I said, I'll include both of them for reference. But yeah, that's going to be all for this one. So let me know what you thought about this one. And if you did like it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.